Welcome back to another reading. We have another preservation brief here, and thought it was worth sharing. This one is about architectural terracotta. Some intriguing data on deterioration problems which are common to terracotta, and then providing methods for determining the extent of that deterioration. It then makes some recommendations for maintenance and repair work, including some indications of replacement materials. This document is dated from 1979 and completed by Detiel Patterson Tiller. It's put out or published by the National Park Service of the United States. I found quite a few more of these briefs on various topics, and will include more in the future for readings. Prepare yourself for an inundation of glazed architectural terracotta mentions. You've been warned. With that, thanks for listening in. Let's begin. The preservation of historical glazed architectural terracotta. Glazed architectural terracotta was significant in the development of important architectural idioms in this country, specifically the Chicago School, the high-rise, and the historical Beaux Arts styles. In fact, glazed architectural terracotta is one of the most prevalent masonry building materials found in the urban environment today. Figure 1. Terracotta detailing. Adaptable to every nuance of color, texture, and modeling, glazed architectural terracotta was ideally suited to satisfy the tastes of an eclectic age. Its popularity was, however, short-lived. It endured only 30 or 40 years after its introduction as a building material, late in the 19th century. Reading on. Popular between the late 19th century and the 1930s, glazed architectural terracotta offered a modular, varied, and relatively inexpensive approach to wall and floor construction. It was particularly adaptable to vigorous and rich ornamental detailing. However, with changing vogues and materials, and architectural styles, and rising production costs, glazed architectural terracotta fell into disfavor and disuse by the mid-20th century. Today, information on the maintenance, rehabilitation, and replacement of glazed architectural terracotta is limited, as are sources of new glazed architectural terracotta. This report, then, will discuss some of the major deterioration problems that commonly occur in historic glazed architectural terracotta, methods of determining the extent of that deterioration, and recommendations for the maintenance, repair, and replacement of the deteriorated historic material. What is terracotta? Generically, the broadest definition of terracotta refers to a high grade of weathered or aged clay, which, when mixed with sand or pulverized fired clay, can be molded and fired at high temperatures to a hardness and compactness not obtainable with brick. Simply put, terracotta is an enriched mottled clay brick or block. The word terracotta is derived from the Latin word terra-cotta, literally cooked earth. Terracotta clays vary widely in color according to geography and types, ranging from red and brown to white. Terracotta was usually hollow cast in blocks, which were open to the back, like boxes, with internal compartments like stiffeners called webbing. Figure 2. Webbing, or the hollow internal compartment construction of glazed architectural terracotta blocks, made them inexpensive to produce, easy to handle, and light in construction. These were significant factors in the popularity of the material in the first decades of this century. Reading on. Webbing substantially strengthened the load-bearing capacity of the hollow terracotta block without greatly increasing its weight. Terracotta blocks were often finished with a glaze, that is, a slip glaze or clay wash, or an aqueous solution of metal salts, was brushed or sprayed on the air-dried block before firing. Glazing changed the color, imitated different finishes, and produced a relatively impervious surface on the weather face of the final product. The glaze on the terracotta unit possessed excellent weathering properties when properly maintained, It had rich color and provided a hard surface that was not easily chipped off. Glazing offered unlimited and fade-resistant colors to the designer. Even today, few building materials can match the glazes on terracotta for the range and, most importantly, the durability of colors. Types of terracotta. Historically, there are 4 types or categories of terracotta which have enjoyed wide use in the history of the American building arts. First is the brownstone, second, fireproof construction, third, ceramic veneer, and fourth, glazed architectural. Brownstone terracotta is the variety of this masonry material used earliest in American buildings, mid to late 19th century. The brownstone type is a dark red or brown block either glazed, usually a slip glaze, or unglazed. It was hollow cast and was generally used in conjunction with other masonry, in imitation of sandstone, brick, or real brown stone. It is often found in the architecture of Richard Upjohn, James Renwick, H. Richardson, and is associated with the Gothic and Romanesque revival movements, through such ornamental detailing as moldings, finials, and capitals. Fireproof construction terracotta was extensively developed as a direct result of the growth of the high-rise building in America. Inexpensive, lightweight, and fireproof, these rough-finished, hollow building blocks were ideally suited to span the I-beam members in floor, wall, and ceiling construction. Figure 3. Fireproof construction terracotta. Perspective and section through fireproof construction terracotta and I-beam detailing in industrial floor construction. Reading on. Certain varieties are still in production today, although fireproof construction terracotta is no longer widely employed in the building industry. Ceramic veneer was developed during the 1930s and is still used extensively in building construction today. Unlike traditional architectural terracotta, ceramic veneer is not hollow cast, but is, as its name implies, a veneer of glazed ceramic tile, which is ribbed on the back in much the same fashion as bathroom tile. Ceramic veneer is frequently attached to a grid of metal ties, which has been anchored to the building. Glazed architectural terracotta was the most complex development of terracotta as a masonry building material in this country. The hollow units were hand-cast in molds or carved in clay and heavily glazed, often in imitation of stone, and fired. Sometimes called architectural ceramics, glazed architectural terracotta was developed and refined throughout the first third of the 20th century and has been closely associated with the architecture of Cass Gilbert, Louis Sullivan, and Daniel H. Burnham. Interesting detail there. That should be a familiar name for those following the Columbian Exposition series. Significant examples in this country include the Woolworth Building, 1913 in New York City, and the Wrigley Building, 1921 in Chicago. Late 19th and early 20th century advertising promoted the durability, impervious, and adaptable nature of glazed architectural terracotta. It provided for crisp, vigorous modeling of architectural details as the molds were cast directly from clay prototypes without loss of refinement. Glazed architectural terracotta could accommodate subtle nuances of modeling, texture, and color. Compared to stone, it was easier to handle, quickly set, and more affordable to use. Thought to be fireproof and waterproof, it was readily adaptable to structures of almost any height. The cost of molding the clay, glazing, and firing the blocks, when compared to carving stone, represented a considerable savings, especially when casts were used in a modular fashion, that is, repeated over and over again. Maintenance of the fired and glazed surface was easy. It never needed paint, and periodic washings restored its original appearance. With the passage of time, many of the phenomenal claims of the early proponents of glazed architectural terracotta have proven true. There are many examples throughout this country that attest to the durability and permanence of this material. Yet present-day deterioration of other significant glazed architectural terracotta resources ultimately, I think that's belie those claims? Unsure. Why? Historically, the lack of foresight or understanding about the nature and limitations of the material has, in many instances, allowed serious deterioration problems to occur that are only now becoming apparent. Characteristics of glazed architectural terracotta as a building material. Glazed architectural terracotta has many material properties similar to brick or stone. It also has many material properties radically different from those traditional masonry materials. It is those differences which must be considered for a better understanding of some of the material characteristics of glazed architectural terracotta when it is used as a building material. Difficult to identify. Glazed architectural terracotta probably comprises one of the largest, if not the largest, constituent material in some of our urban environments today. However, the infinite varieties of glazing have hidden this fact from the casual observer. One of the attractive features of glazed architectural terracotta in its time was that it could be finished, glazed, in exact imitation of stone. In fact, many building owners and architects alike are often surprised to discover that what they presumed to be a granite or limestone building is glazed architectural terracotta instead. Very intriguing. Two separate systems. Historically, glazed architectural terracotta has been used in association with two specific and very different types of building systems, as part of a traditional load-bearing masonry wall and buildings of modest height, and as a cladding material in high-rise construction. As cladding, glazed architectural terracotta often utilized an extensive metal anchoring system to attach it or to hang it onto a wall framing system or superstructure. Figure 4. Typical construction detail of glazed architectural terracotta ornament. Construction detailing was often complex. The terracotta units, number 1, which were laid in mortar, were fitted with holes or slots to receive the metal anchors, number 2, often called Z-straps or light iron, which were often fitted directly to the building frame. Masonry backfill, 3, either brick or poured cement, was laid between the terracotta units, with the building frame encasing the metal anchor. Overhanging or protruding elements were further secured by metal dowels or outriggers, number 4. Reading on. In the first instance, the anchoring was limited. In the second, the anchoring was often extensive and complex. Likewise, in the first instance, deterioration has generally been limited. However, where glazed architectural terracotta was used as cladding, particularly in high-rise construction, present-day deterioration and failure are often severe. Complexity of deterioration. Deterioration is, by nature of the design, infinitely complex, particularly when glazed architectural terracotta has been used as a cladding material. Deterioration creates a domino-like breakdown of the whole system: glazed units, mortar, metal anchors, and masonry backfill. In no other masonry system is material failure potentially so complicated. Poor original design. The root of deterioration in glazed architectural terracotta systems often lies in a misapplication of the material. Historically, glazed architectural terracotta was viewed as a highly waterproof system, needing neither flashing, weep holes, nor drips. This supposition, however, has proved to be untrue, as serious water-related failure was evident early in the life of many glazed architectural terracotta clad or detailed buildings. Common deterioration problems. No one case of deterioration in glazed architectural terracotta is ever identical to another, owing to the infinite number of variations with the material. Original manufacture, original installation, inconsistencies, number of component parts, ongoing repairs, or the various types and sources of deterioration. However, certain general statements may be made on the nature of glazed architectural terracotta deterioration. Material failure can most commonly be attributed to water-related problems. However, less frequent though less severe causes may include faulty original craftsmanship, which is often cited but hard to determine, stress-related deterioration, damage caused by later alterations and additions, or inappropriate repairs. Water-related deterioration. As with most building, conservation, and rehabilitation problems, water is a principal source of deterioration in glazed architectural terracotta. Terracotta systems are highly susceptible to such complex, water-related deterioration problems as glaze crazing, glaze spalling, and material loss, missing masonry units, and deteriorated metal anchoring, among others. Crazing, or the formation of small random cracks in the glaze, is a common form of water-related deterioration in glazed architectural terracotta. When the new terracotta unit first comes from the kiln after firing, it has shrunken, or dried, to its smallest possible size. With the passage of time, however, it expands as it absorbs moisture from the air, a process which may continue for many years. The glaze goes into tension because it has a lesser capacity for expansion than the porous tile body. It no longer fits the expanding unit onto which it was originally fired. If the strength of the glaze is exceeded, it will crack, or craze. Figure 5. Crazing. Water and airborne moisture entering the glazed architectural terracotta causes expansion of the porous clay body, which increases its volume. This, in turn, is sufficient to upset the fit of the glaze and to make it shatter, commonly called crazing. Crazing is a process not unlike the random hairline cracking on the surface of an old oil painting. Both may occur as a normal process in the aging of the material, unless the cracks visibly extend onto the porous tile body beneath the glaze. Crazing should not be regarded as highly serious material failure. It does, however, tend to increase the water absorption capability of the glazed architectural terracotta unit. Spalling. The partial loss of the masonry material itself is like crazing, caused by water, and is usually a result not only of airborne water, but more commonly of water trapped within the masonry system itself. Trapped water is often caused by poor water detailing in the original design, insufficient maintenance, rising damp, or a leaking roof. In most cases, trapped water tends to migrate outward through masonry walls where it eventually evaporates. In glazed architectural terracotta, the water is impeded in its journey by the relatively impervious glaze on the surface of the unit, which acts as a water barrier. The water is stopped at the glaze until it builds up sufficient pressure, particularly in the presence of widely fluctuating temperatures, to pop off sections of the glaze, or glaze spalling, or to cause the wholesale destruction of portions of the glazed architectural terracotta unit itself, material spalling. Glaze spalling may appear as small coin-sized blisters where the glaze has ruptured and exposed the porous tile body beneath. Figure 6. Glaze spalling. Blistering of the glaze, like crazing, is the result of the increase in water in the porous clay body, and the subsequent destruction of the glaze as a result of water migration and pressure. Glaze spalling may also be caused by deterioration of metal anchors behind the terracotta unit. Reading on. This may occur as several spots on the surface, or in more advanced cases of deterioration, it may result in the wholesale disappearance of the glaze. Spalling of the glaze may also be symptomatic of deterioration, rusting, of the internal metal anchoring system which holds the terracotta units together and to the larger building structure. The increase in volume of the metal created by rusting creates increased internal pressures in the terracotta unit, which, in turn, may spall the glaze, or in more extreme cases cause material spalling. Material spalling is a particularly severe situation. Not only is the visual integrity of the detailing impaired, but a large area of the porous underbody, webbing, and metal anchoring is exposed to the destructive effects of further water entry and deterioration. Figure 7. Material spalling. Excessive expansion of the porous tile body caused by water and freezing temperatures produces major material spalling, a situation often difficult to repair. Both glaze and material spalling must be dealt with as soon as possible. Missing units is a serious situation which particularly plagues architectural terracotta systems. Unlike brick or stone, damaged glazed architectural terracotta is exceedingly difficult to replace. New production is extremely limited. Missing units create gaps which increase the structural load on the remaining pieces and also permit water to enter the system. Exposed or freestanding glazed architectural terracotta detailing, balusters, urns, parapet walls, etc., are particularly susceptible to extensive loss of material. Figure 8. Deterioration of exposed detailing. Exposed or freestanding terracotta detailing, parapets, urns, balusters, etc., have traditionally been subject to the most severe vicissitudes of deterioration as a result of freezing temperatures and water. Reading on. These elements face the most severe vicissitudes of water and temperature-related deterioration in direct proportion to the extent of their exposure. The replacement of missing units should be a high priority work item in the rehabilitation of glazed architectural terracotta. Deterioration of metal anchoring. Deteriorated anchoring systems are perhaps the most difficult form of glazed architectural terracotta deterioration to locate or diagnose. Often, the damage must be severe and irreparable before it is noticed on even the most intense prima facie examination. Water which enters the glazed architectural terracotta system can rust the anchoring system and substantially weaken or completely disintegrate those elements. Where water has been permitted to enter the system, some deterioration has more than likely taken place. Partial deterioration results in staining and material spalling. Total deterioration and the lack of any anchoring system may result in the loosening of the units themselves, threatening the architectural or structural integrity of the building. Recently, falling glazed architectural terracotta units have become a serious safety concern to many building owners and municipal governments. Figure 9. Deterioration of metal anchoring and masonry backfill. Trapped water may deteriorate masonry backfill or rust metal anchoring, causing overhanging architectural elements to loosen and drop from the building. This is particularly true when unmaintained roof drainage systems fail and soak the masonry system. Note the exposed metal anchoring. So just this guy right here. Reading on. Early detection of failing anchoring systems is exceedingly difficult. Deteriorated mortar has always been a key to the survival or failure of any masonry system. This is particularly true with the glazed architectural terracotta. In recognition of the fragile nature of the system, the need for ensuring a relatively dry internal system is important. Sound mortar is the first line of defense in terracotta systems. It is a maintenance must. Deteriorated mortar joints are a singular culpable source of water and therefore of deterioration. Mortar deterioration may result from improper original craftsmanship or air and waterborne pollution. More often, however, lack of ongoing maintenance is mainly responsible. Deteriorated mortar should not be overlooked as a major source of glazed architectural terracotta failure. The deterioration of materials adjoining the glazed architectural terracotta, flashing, capping, roofing, caulking around windows and doors, bears significant responsibility in its deterioration. When these adjoining materials fail, largely as a result of lack of maintenance, water-related deterioration results. For instance, it is not uncommon to find wholesale terracotta spalling in close proximity to a window or doorway where the caulking has deteriorated. Stress-related deterioration. Stress-related deterioration of glazed architectural terracotta frequently occurs in high-rise buildings. The evolution of stress-relieving details, flexible joints, shelf angles, etc., occurred late in the development of American building construction. Consequently, most early, continuously clad high-rise buildings, circa 1900 to 1920s, had little or no provisions for normal material and building movement in their original design. The development of large stress-related cracks or wholesale material deterioration is often caused by unaccommodated building frame, shortening under load, thermal expansion and contraction of the facade, and moisture expansion of the glazed architectural terracotta units themselves. Figure 10. Structural cracking. Structural cracking, whether static, non-moving, or dynamic, moving or active, should be caulked to prevent water entry into the glazed architectural terracotta system. Note the exposed webbing. Reading on. Cracks running through many units or stories or large areas of material deterioration often indicate stress-related problems. This sort of deterioration, in turn, permits significant water entry into the terracotta system. Inappropriate repairs. Inappropriate repairs result because using new terracotta for replacement of deteriorated or missing glazed architectural terracotta has generally been impractical. Repairs, therefore, have traditionally been made in brick or cementitious buildups of numerous materials, such as stucco or fiberglass. Some materials are appropriate temporary or permanent replacements, while others are not. These issues are discussed at a later point in this report. However, improper anchoring or bonding of the repair work or visual incompatibility of repairs have themselves, with the passage of time, become rehabilitation problems. Replacement brick that is pulling free, cement stucco that is cracking and spalling, or cement or bituminous repairs that are not visually compatible with the original material. Alteration damage. Alteration damage has occurred as a result of the installation of such building additions as signs, screens, marquees, or bird-proofing. These installations often necessitated the boring of holes or cutting of the glazed architectural terracotta to anchor these additions to the building frame beneath. As the anchoring or caulking deteriorated, or as these elements were removed in subsequent renovation work, these holes have become significant sources of water-related damage to the glazed architectural terracotta system. Deterioration, inspection, and analysis. Certain deterioration in glazed architectural terracotta may be on the building's surface and patently obvious to the casual observer. Crazing, spalling, deterioration of mortar joints. Other deterioration may be internal or within the masonry system and hard to determine. Deterioration of anchoring, deterioration behind the glaze, crumbling of internal webbing. Prima facie, first inspection. Examination may indicate surface deterioration problems, while not revealing others. This demonstrates one of the most frustrating aspects of dealing with deteriorated glazed architectural terracotta, that there are two systems or levels of deterioration, one which is visible and the other which is not. Material failure in glazed architectural terracotta is necessarily complex. For this reason, it is generally advised that the examination and repair of this material should be the responsibility of an experienced professional. Few restorationists have experience in the inspection, repair, and replacement of glazed architectural terracotta. This is certainly never the province of the amateur or the most well-intentioned, but inexperienced architect or engineer. There are some methods of internal and external inspection and analysis which are relatively simple to the trained professional. Other methods, however, are expensive, time-consuming, and only in the experimental stage at this writing. These all generally preclude the use of anyone but an experienced professional. Preliminary cleaning. Before a terracotta building is analyzed for deterioration, it is often advisable, but not always necessary, to clean the surface of the material. This is particularly true when the material has been exposed to the vicissitudes of heavy urban pollution. While most building materials are cleaned for cosmetic purposes, the cleaning of glazed architectural terracotta for the purpose of inspection and analysis may be advised. Dirt on glazed architectural terracotta often hides a multitude of problems. It is only with cleaning that these problems become obvious. Recommended cleaning procedures are covered later in the report. Methods of inspection. Prima facie analysis is the unit-by-unit, first-hand external inspection of the glazed architectural terracotta building surface. Special note of all visible surface deterioration, which can include staining, crazing, spalling, cracking, etc., should be made on elevation drawings. Binoculars are often used where cost, height, or inaccessibility prevent easy inspection. However, much deterioration may go unnoticed unless scaffolding or window washing apparatus is used in a true hands-on inspection of each unit of the facade. Tapping, a somewhat inexact method of detection of internal deterioration, is, nevertheless, the most reliable inspection procedure presently available. Quite simply, tapping is the striking of each unit with a wooden mallet. When struck, an undamaged glazed architectural terracotta unit gives a pronounced ring, indicating its sound internal condition. Conversely, deteriorated units which are failing internally, produce a flat, hollow sound. Metal hammers are never to be used, as they may damage the glazed surface of the unit. Extensive experience is the best teacher with this inspection method. Infrared scanning is only in the experimental stage at this time, but its use seems to hold great promise in locating deteriorated internal material in terracotta. All materials emit heat which can be measured in terms of infrared light. While infrared light cannot be seen by the human eye, it can be measured by infrared scanning. Infrared photography, the kind of infrared scanning, has been of particular use in detecting sources of heat loss in buildings in recent years. Broken or loose internal terracotta pieces have a less firm attachment to the surrounding firm or attached pieces, and therefore have different thermal properties, or temperatures. These temperature differences become evident on the infrared scan and may serve as a fair indication of internal material deterioration in terracotta. Sonic testing has been successfully used for some time to detect internal cracking of concrete members. In the hands of an experienced operator, there are conditions where it can detect internal failure in glazed architectural terracotta. Sonic testing registers the internal configuration of materials by penetrating the material with sound waves and reading the patterns that bounce back from the originating source of the sound. Readings at variance with those from undeteriorated material might indicate collapsed webbing or pools of water in the interior of the terracotta unit. Metal detection is a non-destructive and generally useful way of locating the position of internal metal anchoring. Metal detectors indicate the presence of metal by electromagnetic impulses. These impulses are transmitted onto an oscilloscope where they may be seen, or they are converted to sound patterns, which may be heard by the operator. Original drawings are eminently useful in predicting where internal metal anchoring should be. Metal detectors can confirm that indeed they are still there. Without original drawings, the contractor or architect can still locate the metal anchoring. However, no reading where an anchor would be expected could indicate a missing anchor or one that has seriously deteriorated. The information produced by metal detection is, at best, only rough. However, it is the most viable way of locating the internal metal anchoring without physically removing, thus irreparably damaging, the glazed architectural terracotta units themselves. Laboratory analysis may be carried out on samples of removed original material to find glaze absorption, permeability, or glaze adhesion, or to evaluate material for porosity. These tests are useful in determining the present material characteristics of the historic glazed architectural terracotta and how they may be expected to perform in the future. Maintenance, repair, and replacement. Deterioration in glazed architectural terracotta is, by definition, insidious in that the outward signs of decay do do not always indicate the more serious problems within. It is, therefore, of paramount importance that the repair and replacement of deteriorated glazed architectural terracotta not be undertaken unless the causes of that deterioration have been determined and repaired. As mentioned before, one of the primary agents of deterioration in glazed architectural terracotta is water. Therefore, water-related damage can be repaired only when the sources of that water have been eliminated. Repointing, caulking, and replacement of missing masonry pieces are also of primary concern, where detailing to conduct water in the original design has been insufficient. The installation of new flashing or weep holes might be considered. Where stress-related or structural problems have caused the deterioration of glazed architectural terracotta, the services of a structural engineer should be sought to mitigate these problems. This may include the installation of relieving joints, shelf angles, or flexible joints. In any case, stress-related and structural deterioration, like water-related deterioration, must be stopped before effective consolidation or replacement efforts may begin. Cleaning. The successful cleaning of glazed architectural terracotta removes excessive soil from the glazed surface without damaging the masonry unit itself. Of the many cleaning materials available, the most widely recommended are water, detergent, and a natural or nylon bristle brush. More stubborn pollution or fire-related dirt or bird droppings can be cleaned with steam or weak solutions of muriatic or oxalic acid. A note of caution: any acids, when used in strong enough solutions, may themselves deteriorate mortar and liberate salts within the masonry system, producing a situation called efflorescence. For further information on the situation, refer to Preservation Briefs, the cleaning and waterproof coating of masonry buildings. I may see if I can find that one as well, and I'll include it in upcoming readings. Moving on. Commercial cleaning solutions may be appropriate, but probably are not necessary when water and detergent will suffice. There are, however, certain cleaning techniques for glazed architectural terracotta which are definitely not recommended, and which would damage the surface of the material. These include all abrasive cleaning measures, especially sandblasting, the use of strong acids, particularly fluoride-based acids, high-pressure water cleaning, and the use of metal bristle brushes. All of these techniques will irreparably harm the glaze in one fashion or another, and subsequently expose the porous tile body to the damaging effects of water. It is important to remember that glazed architectural terracotta was designed to be cleaned cheaply and easily. This, in fact, was one of its major assets, and was much advertised in the selling of the material early in this century. Waterproofing. The covering of crazed glazing, see Figure 5, which we've already read through, with waterproof coatings is the subject of an ongoing controversy today. The question involves whether or not the micro cracks conduct substantial amounts of water into the porous tile body. Tests indicate that the glaze on new, unexposed terracotta is itself not completely waterproof. Some testing also indicates that most crazing on historic glazed terracotta does not substantially increase the flow of moisture into the porous tile body when compared to new material. Excessive and serious crazing is, however, an exception, and the coating of those areas on a limited scale may be wholly appropriate. In an effort to stem water-related deterioration, architects and building owners often erroneously attribute water-related damage to glaze crazing when the source of deterioration is, in fact, elsewhere: deteriorated caulking, flashing, etc. The waterproof coating of glazed architectural terracotta walls may cause problems on its own. Outward migration of water vapor normally occurs through the mortar joints in these systems. The inadvertent sealing of these joints in the wholesale coating of the wall may exacerbate an already serious situation. Spalling of the glaze, mortar, or porous body will, more than likely, result. Repointing. Repointing of mortar which is severely deteriorated or improperly or infrequently maintained is one of the most useful preservation activities that can be performed on historic glazed architectural terracotta buildings. Ongoing and cyclical repointing guarantees the long life of this material. Repointing should always be carried out with a mortar which has a compressive strength, measured in psi, or pounds per square inch, lower than the adjacent masonry unit. Hard Portland cement or coarsely screened mortars may cause pointing, loading, and/or prevent the outward migration of the water through the mortar joints, both of which ultimately damage the terracotta unit. Repointing with waterproof caulking, compounds, or similar waterproof materials should never be undertaken because, like waterproof coatings, they impede the normal outward migration of moisture through the masonry joints. Moisture then may build sufficient pressure behind the waterproof caulk and then the glaze on the terracotta to cause damage to the unit itself. Repair of glaze spalling. Glaze spalling is also a highly culpable source of water-related deterioration in glazed architectural terracotta. It is important to coat or seal these blistered areas, referencing figure 6 here, and to prevent further entry of water into the system by this route. All loose or friable material should be removed. This may be done easily by hand. Chisels or similar small tools are most effective. The exposed material is then painted over. At this time, no permanently effective reglazing materials are available. However, there are several acrylic-based, proprietary products and masonry paints which can be used effectively to protect these exposed areas, thus preventing the entry of water. These materials are effective for 5 to 7 years and can be reapplied. They also can be tinted to approximate closely the original glaze color. Repair of minor material spalling. Minor material spalling, where visual or cosmetic considerations are negligible, should be treated in a manner similar to glaze spalling damage. That is, areas where small portions of the body and glaze have spalled and which are far removed from close scrutiny, for example detailing on entablatures, upper story windows, etc., are best remedied by painting with a masonry paint or an acrylic-based proprietary product. Units on which material spalling is easily observed, on the street level, door surrounds, etc., and on which visual integrity is a consideration, may be better replaced. Patching is not appropriate. Stucco-like or cementitious buildups are difficult to form satisfactorily, safely and compatibly in situ to replace missing pieces of glazed architectural terracotta. Cementitious repairs never satisfactorily bond to the original material. The differential expansion coefficients of the two materials, the repair and the original, preclude a safe, effective, and long-term attachment. Repair of major spalling. Glazed architectural terracotta units which have spalled severely, thereby losing much of their material and structural integrity in the wall, should be replaced. Partial in situ repair will not be long-lasting and may, in fact, cause complicated restoration problems at a later date. Appropriate methods of replacement are discussed at a later point in this report. Temporary stabilization. Stabilization measures are necessary when deterioration is so severe as to create a situation where pieces of glazed architectural terracotta may fall from the building. This is a particular concern with greatly exposed detailing: cornices, balconies, balustrades, urns, columns, buttresses, etc. Restoration work on these pieces is expensive and often must be carried on over a period of time. Unstable terracotta pieces are often removed or destroyed in lieu of such measures. This is particularly true in areas of heavy traffic-related vibrations or in earthquake zones. They are, however, less severe measures which may be employed on a temporary basis. Substantial success has been achieved in securing unstable glazed architectural terracotta pieces with metal strapping and a nylon net. Figure 11. Temporary stabilization measures. Falling glazed architectural terracotta detailing has become a source of concern, particularly in dense urban areas and locations of high seismic activity. Nylon netting and metal strapping, while not seen as a permanent preservation measure, do offer temporary alternative to the removal of these elements. Reading on. While these measures should not be seen as permanent preservation solutions, they do offer temporary alternatives to the wanton destruction of significant glazed architectural terracotta, detailing in the name of public safety and local code compliance. Repair of addition and structural damage. Holes, sign anchors, slots for channel steel, or structural cracking in the surface of glazed architectural terracotta cladding should be permanently sealed with a material that will expand with the normal dynamics of the surrounding material, yet effectively keep water out of the system. Any one of a number of commercially available waterproof caulking compounds would be appropriate for this work. Holes and static, non-moving, cracks may be caulked with butyl sealants or acrylic latex caulks. For dynamic, moving or active cracks, the polysulfide caulks are most often used, although others may be safely employed. It is, however, important to remember that these waterproof caulking compounds are not viable repointing materials and should not be used as such. Temporary replacement. Temporary replacement measures should be implemented when missing units are scheduled to be replaced, but work cannot be undertaken immediately. Lengthy delivery time, prorating of work, or seasonal considerations may postpone replacement work. Severe deterioration should at least be ameliorated until work can begin. Temporary repointing, removal, and saving of undamaged units to be reset later, or temporary installation of brick infill to retard further deterioration might be considered. Removing earlier repairs. Removing earlier repairs may be necessary when the work has either deteriorated or has become visually incompatible. Cementitious stucco, caulkings with black bituminous compounds, or brick repair work may become structurally or visually unstable or incompatible and should be removed and properly rehabilitated. Replacement of glazed architectural terracotta. Replacement of severely spalled, damaged, or missing glazed architectural terracotta elements is always difficult. Certainly, in-kind replacement is advisable, but it has a number of drawbacks. Stone, fiberglass, and precast concrete are also viable choices, but like in-kind replacement also have their inherent problems. Several notes on replacement. When replacing glazed architectural terracotta, all of the original deteriorated material should be completely removed. Aft bricks or similar cosmetic replacement techniques are not advised. When possible, and where applicable, replacement units should be anchored in a manner similar to the original. Both structural and visual compatibility are major considerations when choosing replacement materials. Removing and re-anchoring damaged glazed architectural terracotta is an extremely difficult, if not impossible task. Interesting. The complexity of the interlocking system of masonry units, backfill, and metal anchoring system precludes the removal of the glazed architectural terracotta unit without destroying it. Re-anchoring deteriorated units is likewise impossible. Therefore, if the terracotta in question is loose, severely deteriorated, or its structural integrity in serious question, it is best removed and replaced. In-kind replacement is possible today, but only on a limited basis. Most new glazed architectural terracotta is machine-made, not handmade as the original. Thus, the porous tile body of the new material tends to be more uniform but less dense, and often not as durable. The glaze on the new glazed architectural terracotta tends to be thinner than on the older material, and subsequently more brittle. Machine processing has also produced a glaze that is uniform in color as opposed to historic glazes, which were slightly mottled and therefore richer. Visual compatibility is an important consideration when replacing in-kind. Only a fairly limited inventory of in-kind pieces is presently available for replacement, such as plain ashlar blocks and the simpler details such as cappings and sills. When deterioration severely damages the more ornate pieces, urns, cartouche work, balusters, etc., either expensive hand casting or alternative materials must be sought. There is a tendency today to replace damaged ornamental work with simpler, cheaper, and more readily available units. This decision cannot, however, be supported, as the removal of this work inevitably diminishes the character and integrity of the building. Another major consideration in choosing in-kind replacement is the question of delivery time, which is often quite lengthy. If new glazed architectural terracotta is chosen as a replacement material, the architect or building owner should plan far in advance. Stone may be a suitable replacement material for damaged glazed architectural terracotta. Its durability makes it highly appropriate, although the increase in weight over the original hollow units may be of some concern. The fact that historic glazed architectural terracotta was glazed in imitation of stone, however, may make the choice of stone as a replacement material a fortuitous one. Metal anchoring may be accommodated easily in the carving. Cost, however, is the major drawback in stone replacement, particularly where rich detailing must be carved to match the original. Fiberglass replacement is a viable alternative, particularly when rich and elaborate ornamentation has to be duplicated. Casting from original intact pieces can produce numerous sharp copies of entablatures, moldings, balusters, voussoirs, etc. Anchoring is easily included in casting. Significant drawbacks in using fiberglass replacement are color compatibility, fire code violations, and poor weathering and aging properties. The appropriate coloring of fiberglass is exceedingly difficult in many instances. Painting is often unsatisfactory as it discolors at a rate different than that of the historic glazed original. While fiberglass casting is lighter than the original units, and therefore of great interest in the rehabilitation of buildings in areas of high seismic activity, many fire code requirements cannot be met with the use of this material. Precast concrete. Precast concrete units show great promise in replacing glazed architectural terracotta at this writing. Precast concrete units can, like fiberglass, replicate nuances of detail in a modular fashion. They can also be cast hollow, use lightweight aggregate, and be made to accommodate metal anchoring when necessary. Concrete can be colored or tinted to match the original material with excellent results. It is cost-effective, and once production is in process, precast concrete can be produced quickly and easily. Experience shows that it is advisable to use a clear masonry coating on the weather face of the precast concrete units to guarantee the visual compatibility of the new unit, to prevent moisture absorption, to obtain the proper reflectivity in imitation of the original glaze, and to prevent weathering of the unit itself. Precast concrete replacement units are presently enjoying great use in replicating historic glazed architectural terracotta and show promise for future rehabilitation programs. Once the replacement material is selected, new glazed architectural terracotta, stone, precast concrete, or fiberglass, it must be re-anchored into the masonry system. Original metal anchoring came in numerous designs, materials, and coatings, ranging from bituminous-coated iron to bronze. While most of these anchors are no longer available, they may be easily replicated in large quantities, either in the original material, when appropriate, or out of more durable and available metals such as stainless steel. Since the masonry backfill is already in place in the historic building, the new replacement unit with anchoring may simply be fitted into the existing backfill by boring a hole or slot for anchor and bedding the anchor and the unit itself in mortar. When replacing historic glazed architectural terracotta, which originally employed metal anchoring, it is important to replace that anchoring when replacing the unit. Serious problems may result if anchoring is omitted in restoration when it was used originally. It is erroneous to assume that mortar alone will be sufficient to hold these replacement pieces in place. And to end it off here, we have a small summary. Today, many of this country's buildings are constructed of glazed architectural terracotta. However, many of these are in a state of serious deterioration and decay. Glazed architectural terracotta was, in many ways, the wonder material of the American building industry in the late 19th century and during the first decades of the 20th century. New technology and methods of rehabilitation now hold promise for the restoration and rehabilitation of these invaluable and significant resources. Restoration, rehabilitation work on glazed architectural terracotta is demanding and will not tolerate halfway measures. Today's preservation work should equal the spirit, attention to detail, pride in workmanship, and care which characterized the craftsmanship associated with this widely used, historic masonry material.